Module 4, Lecture A, Reusable Functions. By the end of this lecture, you will be able to define functions that perform specific civil engineering calculations, use parameters and return values to make calculation functions reusable, and document and test functions with representative engineering inputs. Function design, specific calculations. When defining a function for a civil engineering task, keep it focused on the essential steps needed to produce one clear output. A trench volume function should handle trench geometry, not scheduling or equipment decisions. And a beam load function should focus on span and loading, not full structural design. This keeps functions easier to test, maintain, and combine into larger analyses such as design checks or quantity takeoffs. Define each function around one clear civil engineering task and one clear output. A trench volume function should focus on trench geometry, while a beam load function should focus on span and loading, not unrelated design or planning details. Keeping functions small and focused makes them easier to test, maintain, and reuse as reliable building blocks in larger engineering analyses. In civil engineering, narrowly defined calculation functions make assumptions about units, materials, and limits more visible. A runoff estimate may be useful for early studies, while a pavement volume calculation may rely on uniform thickness, so each function should be used only within its intended scope. This discipline helps students identify key quantities, choose inputs, apply methods correctly, and produce results that support sound decisions. Python code, specific calculations. A good engineering function should focus on one clear question. Defining its inputs and outputs makes it easier to reuse, and small tests help confirm that its calculations are correct. The footing area function takes the footing's length and width in meters and first checks that both values are positive. If either dimension is 0 or negative, it raises an error because the inputs are not physically valid. When the dimensions are valid, it multiplies the length by the width and returns the area in square meters. The function finds a footing's area by multiplying its length and width in meters, producing a result in square meters. It then returns that area so it can be used elsewhere in the program. The function calculates the concrete volume needed for a slab, using the slab area and thickness. Before doing the calculation, it checks that both inputs are positive. If either value is 0 or negative, it raises an error to prevent an invalid calculation. The calculation first converts the slab thickness from centimeters to meters, so the units match the area in square meters. It then multiplies the area by the converted thickness to find the slab's volume in cubic meters, and returns that result. The axial stress function calculates stress using a load in kilonewtons and a cross-sectional area in square millimeters. Before calculating, it checks that the area is positive and raises an error if the area is 0 or negative. This prevents invalid inputs from producing a meaningless result. The function calculates axial stress by first converting the applied load from kilonewtons to newtons. It then divides that load by the cross-sectional area in square millimeters, producing stress in megapascals. The computed stress value is returned for use elsewhere in the program. These examples use simple engineering functions to calculate footing area, concrete slab volume, and axial stress. The inputs include typical dimensions, slab thickness, load, and member area, with unit conversions handled inside the relevant functions. Together, the calculations help check that the engineering inputs and results are reasonable. We print the key engineering results to quickly check the calculations. The footing area is shown in square meters. the slab volume in cubic meters, and the axial stress in megapascals, each rounded to 2 decimal places. This makes the outputs clear, readable, and easy to verify. The script checks 3 basic engineering calculations: footing area from positive length and width, concrete slab volume using thickness converted to meters, and axial stress from load divided by cross-sectional area. It then runs sample tests and prints the results in square meters, cubic meters, and megapascals to confirm the calculations are reasonable. Parameter planning. Parameter planning means deciding what information a function needs to perform a civil engineering calculation correctly. Before coding, define the known inputs, the required values, and any assumptions that should be made clear. For example, volume or pavement calculations depend on dimensions such as length, width, depth, area, or thickness. Careful input choices make the function match the engineering task and avoid vague or hidden assumptions. Choose function parameters that match the needed calculation detail and the way engineers actually manage data. Include only inputs that change between cases, such as key loading, geometry, site, or material conditions, while avoiding irrelevant details that make the function harder to use. The function should expose important engineering choices for review, rather than hiding decisions that may need adjustment. Parameter planning makes repeated engineering calculations clearer, more consistent, and easier to reuse. By choosing inputs carefully, the same function can handle different cases without rewriting the calculation, which reduces errors and improves transparency. It also helps clarify units and assumptions, making the work easier to review, test, and adapt as project conditions change. Python code parameter planning. Before writing functions, plan the key parameters they will use. In civil calculations, make assumptions clear and visible so results can be checked. To make functions reusable, define their inputs clearly from the start. Define a footing volume function using length and width in feet and depth in inches. Convert the depth to feet by dividing by 12. Then multiply length, width, and depth to get the volume in cubic feet. The code converts volume from cubic feet to cubic yards by dividing by 27, since 1 cubic yard contains 27 cubic feet. It then returns the converted value for later use or display. The method calculates asphalt mass in tons using the area, thickness, and density. It first converts the thickness from centimeters to meters, so the units match, then multiplies the area by this thickness to find the asphalt volume in cubic meters. This volume is then ready to be used in the mass calculation. The calculation finds mass by multiplying volume by density, giving a result in kilograms. It then converts kilograms to tons by dividing by 1,000. This makes the mass easier to use for large-scale quantities, such as those common in civil engineering. The example calculates 2 common construction quantities using helper functions. One function estimates the concrete volume for a footing from its length, width, and depth, returning cubic yards. Another calculates the mass of an asphalt layer from its area, thickness, and density, returning tons. These results can then be used as engineering inputs for later analysis. The code displays the calculated concrete volume for the footing in cubic yards and the asphalt layer mass in tons. Both results are rounded to 2 decimal places, making the output clear and easy to check. The code emphasizes planning parameters carefully by treating anything that may change in a project as a parameter. This makes the project more flexible and easier to understand. It also keeps unit conversions clear inside each function, helping readers see how units are handled and reducing mistakes. This script uses predefined functions to calculate construction quantities with clear parameters and visible unit conversions. One function finds a concrete footing volume from mixed foot and inch dimensions, producing about 5.33 cubic yards. Another calculates asphalt mass from area, thickness, and density, producing about 8.64 tons. Reusable calculations. Reusable calculations help civil engineers apply the same analysis to different project conditions, such as changes in location or materials. A well-designed function captures the engineering method once and adapts it to new inputs. This keeps work organized, makes reviews easier, and reduces errors by separating the general calculation process from each specific case. Reusable calculation functions should express the core engineering idea without being tied to one project detail. Avoid building a function around a single pipe size, soil weight, or example value. Instead, let project data vary so the same calculation can apply in different contexts. Good functions focus on the essential quantities the engineering case requires, while keeping adaptable details as inputs. Reusable calculations can save time and improve engineering judgment when they are clearly defined and used appropriately. They should match their assumptions, use consistent units and conventions, and not be mistaken for a full design process when they are only meant for quick estimates. With clear names and focused scope, they support faster comparisons, sensitivity checks, fewer errors, and more transparent results. Python code. Reusable calculations. Reusable functions help keep engineering calculations organized and adaptable. Parameters allow one method to work across many situations, while return values make results easier to test and reuse later. The concrete volume function calculates how much concrete is needed from a space's length, width, and thickness, all measured in meters. Before calculating, it checks that every dimension is positive. If any value is 0 or negative, it raises an error to prevent an invalid physical volume calculation. The function finds the concrete volume by multiplying the length, width, and thickness in meters, producing a result in cubic meters. It then returns that value so the program can use it elsewhere. The stopping sight distance function estimates how far a vehicle needs to stop safely using speed, reaction time, and deceleration. Before calculating, it checks that all three inputs are positive. If any value is 0 or negative, it raises an error, so the calculation only uses valid, realistic data. The code first converts speed from miles per hour to feet per second, since the later calculations use feet and seconds. It then finds the reaction distance by multiplying that speed by the driver's reaction time. This gives the distance the vehicle travels before braking begins. The calculation estimates how far a vehicle needs to stop. It finds braking distance from the vehicle's speed and deceleration based on basic physics, then adds the driver's reaction distance. The result is the total stopping sight distance, or the distance traveled before the vehicle comes to a complete stop. We test the concrete volume function using two typical slab examples. First, it calculates the sidewalk volume from a length of 12 meters, a width of 1.5 meters, and a thickness of 0.1 meters. Then it calculates the footing volume using 8 meters by 2 meters by 0.45 meters. These checks confirm that the function gives concrete volumes in cubic meters for common slab dimensions. The stopping sight distance function is tested for two roadway conditions. For an urban case, it uses a speed of 35 miles per hour, a reaction time of 2.5 seconds, and a deceleration rate of 11.2 feet per second squared. Pause. The same reaction time and deceleration rate are then used for a highway speed of 65 miles per hour, producing a longer stopping distance because the vehicle is moving faster. The output summarizes key engineering results for quick checking. It reports the concrete volumes for the sidewalk and footing to 2 decimal places in cubic meters, then gives the urban and highway stopping site distances rounded to the nearest foot. The code uses assertions as simple checks on the concrete volume calculations. It verifies that the sidewalk volume is between 1.7 and 1.9 cubic meters, and that the footing volume is between 7.1 and 7.3 cubic meters. These range checks help confirm the results are reasonable and catch possible calculation errors. The code validates the stopping site distance calculations by checking that the urban value is positive and that the highway value is larger. If both checks pass, it prints a message confirming the representative function test succeeded, indicating the reusable calculations are behaving correctly. The script provides 2 engineering calculation tools. One estimates concrete volume from positive dimensions in meters, and the other estimates stopping site distance from positive speed, reaction time, and deceleration values. It tests them with sample sidewalk, footing, urban, and highway cases, producing about 1.8 cubic meters for the sidewalk and 7.2 cubic meters for the footing. The stopping distance results are checked against expected ranges, with the highway distance confirmed to be greater than the urban distance. If all checks pass, the script prints a success message. Reusable engineering formulas. Function inputs. In engineering, formulas depend on meaningful inputs to produce useful results. In civil engineering, these inputs may be dimensions, material properties, rainfall intensity, or drainage area, depending on the problem. Using inputs instead of fixed values makes a method flexible, so the same calculation can apply to many projects rather than just one specific case. Good function inputs make calculations clearer, easier to test, and harder to misuse. Each input should be explicit and based on values engineers can find in drawings or specifications, such as dimensions or material details. This transparency helps others judge whether the values are appropriate and makes it easier to repeat the same method with different design choices. Good engineering calculations depend on clear, accurate function inputs. Values should use consistent units, appropriate ranges, and reliable sources, because mixing units or using uncertain estimates can lead to errors. Well-designed inputs reduce confusion while keeping functions flexible, adaptable, and useful across different design and analysis tasks. Python code. Function inputs. Functions are most useful when they take clear engineering inputs, use parameters to make formulas reusable across projects, and return results that can guide later decisions. The footing volume function calculates the concrete volume needed for a footing, using its length, width, and depth in meters. Before calculating, it checks that all dimensions are positive, since 0 or negative values are not valid for a physical structure. If any value is invalid, the function raises an error, so only reliable inputs are used. The function first checks that all footing dimensions are positive, raising an error if any are 0 or negative. It then calculates the volume in cubic meters by multiplying the length, width, and depth, and returns the result for use elsewhere in the program. The runoff flow function estimates peak flow using the rational method. It uses the runoff coefficient, rainfall intensity, and drainage area as inputs. Before calculating, it checks that the runoff coefficient is between 0 and 1, since it represents the fraction of rainfall that becomes runoff. The code validates the inputs before performing hydrological calculations. It ensures the runoff coefficient is between 0 and 1 and checks that rainfall intensity and area are both positive. If any value is outside these limits, it raises an error to prevent unrealistic or meaningless results. The code estimates peak flow with the rational method by combining the runoff coefficient, rainfall intensity, and drainage area. The result is a flow rate in cubic feet per second, which can then be used in later calculations. The examples use a footing volume function to calculate concrete volume for 2 footings, a smaller one measuring 2.4 by 1.8 by 0.5 meters, and a larger one measuring 3 by 2.2 by 0.6 meters. They also use a runoff flow function to estimate peak flow for a parking lot, based on a runoff coefficient of 0.85, rainfall intensity of 2.1 inches per hour, and an area of 4.5 acres. The output reports 3 calculated engineering values in a clear format: the small footing volume, the large footing volume, and the parking lot runoff flow. Each result is rounded to 2 decimal places and labeled with the correct units, making the values easy to compare. The runoff flow function is used with a runoff coefficient of 0.55, rainfall intensity of 1.8 inches per hour, and an area of 8 acres to estimate peak runoff using the rational method. The calculated flow is then displayed to 2 decimal places in cubic feet per second. This shows how the same method can be reused with different inputs to evaluate runoff for different site conditions. This script calculates 2 common engineering quantities: concrete footing volume and peak runoff flow, using the rational method. It validates that dimensions, rainfall intensity, and area are positive, and that the runoff coefficient is between 0 and 1. When run, it prints sample results for 2 footings and 2 runoff cases, with outputs in cubic meters and cubic feet per second. Parameters and returns. Parameters make engineering functions adaptable by letting them accept inputs such as span length, load intensity, or catchment size. The function then returns a useful result, such as flow rate or factor of safety, that can support further analysis. Together, parameters and return values make calculations flexible and reusable across different engineering problems. In civil engineering, a good function keeps the calculation method separate from the inputs that change. For a concrete weight calculation, the same process can use different dimensions and material properties through parameters. This makes the function flexible, reduces repeated work and errors, and lets the results support tasks like load summaries or cost estimates. Design functions around how engineers use results. Inputs should include only the essential information needed for the calculation, and outputs should support the next decision, such as returning a pavement thickness or a slope safety factor. Clear inputs, predictable outputs, and a focused purpose make functions reliable parts of larger engineering analyses. Python code, parameters and returns. Functions help make engineering calculations reusable. Parameters bring in the project details that can change, and return values provide results that can be used for later decisions. The concrete weight function calculates the weight of a concrete element in kilonewtons. It uses the element's length, width, and depth in meters, along with an optional unit weight that defaults to 24 kilonewtons per cubic meter. This makes it easy to estimate concrete weight while allowing the unit weight to be adjusted when needed. The calculation first finds the concrete element's volume by multiplying its length, width, and depth in meters. It then multiplies that volume by the concrete's unit weight to get the total weight in kilonewtons. The function returns the calculated weight of a concrete element in kilonewtons. This makes the result available for other parts of the program, so the same function can be reused with different inputs in larger calculations. The rational runoff function estimates peak water runoff in cubic meters per second. It uses the drainage area, rainfall intensity, and runoff coefficient to calculate how much rainfall becomes flow. The result comes from multiplying these inputs by a conversion factor and returning the estimated flow rate. The code estimates peak runoff flow in cubic meters per second using the rational method. It combines a constant conversion factor with the runoff coefficient, rainfall intensity, and area, then returns the calculated flow rate for use elsewhere in the program. The calculations estimate 2 concrete weights and 1 drainage flow. A concrete beam measuring 6 meters by 0.3 meters by 0.5 meters is evaluated for weight in kilonewtons, while a parking lot runoff calculation uses an area of 1.8 hectares, rainfall intensity of 65 millimeters per hour, and a runoff coefficient of 0.85 to find flow in cubic meters per second. A smaller concrete slab, 4 meters by 3 meters by 0.15 meters, is also evaluated for weight in kilonewtons. The results are printed in clear engineering units. The concrete beam and small slab weights are shown in kilonewtons to 2 decimal places, and the parking lot runoff is shown in cubic meters per second to 3 decimal places. These returned values can then be stored, compared, or reused for later analysis and decision-making. The script provides 2 simple engineering calculation tools. One estimates concrete weight from volume and unit weight, and the other estimates peak runoff using the rational method. It then tests them on a beam, a parking lot, and a small slab. The printed results are about 72 kilonewtons for the beam, 0.31 cubic meters per second for the runoff, and 43 kilonewtons for the slab, ready for later use or analysis. Returned calculation results. Functions should return calculation results so other parts of a program can store, display, or use them in later computations. In civil engineering, this supports workflows where one result, such as a beam tributary area estimate, feeds into load calculations or design checks. Returning values is more useful than only printing them because it makes the logic reusable and supports reliable quality control. A function's output should be clear, predictable, and matched to its purpose. Simple engineering calculations may return one result, while others may return several related values. Keeping units, precision, and format consistent makes functions easier to understand, reuse, and trust in different contexts. When a function returns a result, engineers can test it against known values or manual calculations to confirm accuracy. This matters in civil engineering because results often need to be compared across design options and edge cases. Returning values also makes functions reusable parts of a larger, repeatable workflow for different projects. Python code. Returned calculation results. Functions return results that can be reused in later engineering work. These returned values make it possible to check outputs, compare cases, and apply results from hydraulic calculations without repeating the work. The runoff flow function calculates water runoff in cubic feet per second using 3 inputs: a runoff coefficient, rainfall intensity, and area. It multiplies these values together and returns the resulting flow for use elsewhere in the program. The pipe capacity function calculates a pipe's flow rate in cubic feet per second. It uses the pipe's cross-sectional area and the fluid's velocity, multiplies them together, and returns the resulting capacity for use elsewhere in the program. We set the key inputs for the runoff calculation: a runoff coefficient of 0.75, rainfall intensity of 2.8 inches per hour, and a site area of 4 acres. These values will be used to estimate the runoff flow. The runoff flow result is stored as the design flow, so it can be reused later. This value comes from the runoff flow function, which uses the site coefficient, rainfall intensity, and site area. Saving it makes later calculations and comparisons clearer and more efficient. Set the pipe's cross-sectional area to 1.8 square feet and the fluid velocity to 5.2 feet per second. Then, use the pipe capacity function to calculate the pipe's flow capacity in cubic feet per second. This result is compared with the design flow to check whether the pipe can handle the expected runoff. To check the design, compare the pipe's available flow capacity with the required design flow. The difference is the margin, showing how much extra capacity remains or how much capacity is lacking. If the margin is 0 or positive, the design passes. If it is negative, the design needs review. The output summarizes the engineering check by showing the calculated runoff flow, the pipe capacity, and the remaining capacity margin, all rounded to 2 decimal places in cubic feet per second. It then reports a design status of pass or review, indicating whether the pipe can handle the expected flow or needs further evaluation. This script estimates whether a drainage pipe can handle a design runoff flow. It calculates runoff from rainfall intensity, area, and a runoff coefficient, then calculates pipe capacity from flow area and velocity. It compares the two values, reports the remaining capacity margin, and prints whether the design passes or needs further review. Testing functions. Representative test cases. Representative test cases help confirm that an engineering function works reliably in realistic situations, not just ideal examples. In civil engineering, tests should use practical field values, typical and boundary conditions, and relevant design scenarios, such as different footing sizes or shapes. The goal is to catch flawed assumptions or calculation errors, while showing the function is dependable for ordinary use, without trying to test every possible input. Good test cases should include both routine inputs and edge cases. Routine cases check that a function works for typical engineering problems, while edge cases test its behavior near limits, where hidden errors often appear. Results should also be checked independently, so testing becomes part of sound engineering reasoning, not just a programming step. Representative test cases show what a function is meant to handle and help future users trust its results. For engineering calculations, tests should use realistic inputs, correct units, and expected outputs to confirm the function works under its stated assumptions. They also help reveal when assumptions are violated, supporting quality assurance and making code more practically reliable. Python code, representative test cases. Representative tests help confirm that engineering functions are reliable enough to reuse. Each test case should have a known expected result, and passing these tests builds confidence in the function's correctness. The footing volume function calculates the volume of a rectangular footing using its length, width, and depth in meters. It first checks that all 3 dimensions are positive, raising an error if any value is 0 or negative. When the inputs are valid, it returns the volume by multiplying the 3 dimensions together. The code verifies that the footing's length, width, and depth are all positive before doing any calculations. If any dimension is 0 or negative, it raises an error to stop invalid physical values from being processed. The code finds the volume of a rectangular footing by multiplying its length, width, and depth in meters. The result is the volume in cubic meters, which helps estimate the amount of concrete needed for construction. A set of test cases is created to check the concrete volume function. Each case includes a brief scenario name, the footing's length, width, and depth in meters, and the expected volume in cubic meters. These examples, such as small building and commercial footings, help confirm that the function gives correct results for typical engineering situations. This test case checks the volume calculation for a shallow strip footing. It stores a descriptive name, the footing's length, width, and depth in meters, and the expected volume in cubic meters. These values are used to confirm that the volume calculation function returns the correct result. The process begins by setting a pass counter to 0, then looping through each test case. For each one, the needed values are unpacked, including the case name, dimensions, and expected volume. This lets each calculated volume be checked against its expected result. The code calculates a footing's volume from its length, width, and depth, returning the result in cubic meters. It then compares this calculated volume with the expected value by finding the absolute difference, which shows how accurate the volume calculation is. The code verifies that the volume error is smaller than a very tiny tolerance, 1 × 10⁻⁹. If so, the calculated volume is close enough to the expected value, and the test is counted as passed. This test checks an invalid footing dimension by using a depth of 0, which is not physically possible. The volume calculation should reject this non-positive value by raising a value error. If that happens, the test records that the edge case was handled correctly. If not, it shows a problem in the validation logic. The output summarizes the concrete volume tests by reporting how many routine cases passed and confirming that the invalid 0 depth input was handled correctly. It also notes that the tests used metric dimensions with results that can be checked manually, supporting the reliability of the testing process. The script calculates the volume of a rectangular footing in cubic meters and requires all dimensions to be positive. It verifies the calculation with several test cases, using a tight tolerance to compare expected and actual results. All normal tests pass, and a 0 dimension correctly triggers an error. Overall, the results confirm that the function is reliable for practical engineering use. Representative test cases. When testing civil engineering functions, use inputs that reflect real project conditions, not arbitrary values. Dimensions, rainfall intensity, drainage area, and similar inputs should match the scale and context of the application. This helps confirm that results are not only technically correct, but also practical, and they should be checked against hand calculations or trusted examples. When testing functions, include ordinary cases, boundary cases, and unusual but realistic cases. Ordinary cases confirm the function works in typical situations, while boundary cases check behavior near limits where mistakes are common. Unusual cases test rare but possible conditions. Avoid unrealistic inputs unless you are specifically testing that the function detects invalid data instead of returning misleading results. Test case documentation should explain not only the inputs and expected outputs, but also why each case matters. This helps others understand what the function has been verified to handle and what assumptions limit its use. For example, tests should show whether a pavement material or water demand function applies across relevant project types and scales. Clear documentation supports safe reuse and keeps calculations credible within their intended scope. Python code. Representative test cases. Representative tests check that reusable engineering functions work correctly under realistic project conditions. Including expected values makes the results easier to verify. The footing volume function calculates a footing's volume using its length, width, and depth in meters. These dimensions are grouped together so they can be checked easily before calculation. This validation ensures all values are positive, helping prevent invalid inputs from causing problems later. The code verifies that every dimension is positive before continuing. If any dimension is 0 or negative, it raises an error to prevent invalid measurements from being used in later calculations. The function calculates footing volume by multiplying its length, width, and depth, all measured in meters. The result is the total volume in cubic meters, which is important for basic engineering calculations. The test cases list stores sample scenarios for the footing volume function. Each scenario includes a test name, the footing's length, width, and depth in meters, and the expected volume in cubic meters. These expected results are used to check whether the function calculates volumes correctly across realistic conditions. The process begins by setting a pass counter to 0 to track successful tests. Each test case is then checked by reading its dimensions and expected volume, calculating the actual volume with the footing volume function, and comparing the result to the expected value. The test compares the actual and expected volumes using a small tolerance to avoid failures from minor floating point errors. If the result is close enough, the test is counted as passed by adding 1 to the total number of successful tests. The code compares each test result with its expected value and marks it as pass when they match, or check when they do not. It then prints a clear summary for each test, including the test name, calculated volume, expected volume, and status. This makes it easy to review whether the function is producing the correct results. This example tests the footing volume function with an invalid dimension of 0. Because the function requires all dimensions to be positive, it raises a value error, which is caught by the error handling block. The result shows that invalid input is rejected safely, making the function more robust for real use. This code checks whether the footing volume calculation rejects invalid dimensions. If a value error occurs because a dimension is 0 or negative, the program catches it and prints a message confirming the input was properly rejected. This lets the program handle expected errors cleanly instead of crashing. The code prints a short test summary showing how many representative cases passed out of the total. This gives a quick view of the function's reliability across the tested conditions. This script calculates footing volume from length, width, and depth while rejecting any non-positive dimensions. It tests the calculation against several expected results and reports whether each one passes or needs checking. It also confirms that invalid input correctly raises an error, then prints a final summary of how many tests passed. Representative test cases. Representative test cases help engineers check that a function works across realistic situations, not just one example. A runoff estimate should be tested for different site types, and a concrete weight calculation should use varied dimensions. The goal is not to test every possible value, but to choose inputs that reflect sound engineering judgment and build confidence in the function's reliability. Good representative tests should cover normal, edge, and invalid cases. Normal tests use typical engineering values. Edge tests check boundary conditions where mistakes are likely, and invalid tests confirm the system rejects unrealistic inputs. Together, these cases support accurate results and help prevent engineering errors. Representative test cases should clearly show a function's purpose, realistic inputs, and expected results that can be checked by calculation, benchmarks, or expert judgment. Engineering functions, such as earthwork volume or structural demand calculations, should be tested with both simple and more realistic cases against known results. Good documentation also states assumptions, such as units and rounding, since many errors come from misunderstandings rather than the formulas themselves. Python code, representative test cases. Representative tests increase confidence in the engineering work by checking important cases with a clear, documented purpose. Invalid inputs should also be tested, so they fail in a clear and expected way. The concrete volume in cubic meters function calculates concrete volume from length, width, and thickness in meters. It first makes sure all three dimensions are positive, raising an error if any value is 0 or negative. When the inputs are valid, it multiplies the three dimensions and returns the volume in cubic meters. The code validates that length, width, and thickness are all positive measurements. If any value is 0 or negative, it raises an error to prevent invalid concrete volume calculations. The function finds the concrete volume in cubic meters by multiplying the length, width, and thickness. This combines the surface area with the depth to represent the full three-dimensional volume needed for engineering calculations. We are creating test cases for a concrete volume calculation function. Each case includes a descriptive name, the slab dimensions in meters, and the expected volume in cubic meters. This makes it easy to check whether the function returns the correct result for known inputs. This test case checks a strip footing volume calculation using dimensions of 12 meters by 0.6 meters by 0.3 meters. The expected concrete volume is 2.16 cubic meters, helping confirm that the volume calculation works for a typical engineering example. This test case checks a thin concrete repair calculation. It uses length, width, and thickness values of 2 meters, 1.5 meters, and 0.05 meters, with an expected volume of 0.15 cubic meters. It is one entry in a set of tests used to confirm that the concrete volume function gives accurate results. The process begins by setting a pass counter to 0, then checking each test case in turn. For every case, the concrete volume function is called with that case's dimensions to calculate the expected volume and help determine whether the test passes. To handle small rounding errors, the test compares the calculated result with the expected value using a very tiny tolerance. If the difference is within that tolerance, the test is counted as passed. The true or false result is converted to 0 or 1 and added to the total number of successful tests. This line summarizes each test case by showing the case name, expected volume, calculated result, and pass status. It helps reviewers quickly check whether the function produced the expected output. An invalid input test checks that the concrete volume calculation rejects errors properly. It uses a negative width, which should not be allowed, so the function raises a value error. The surrounding error handling catches the exception and prints the message, confirming that the bad input was handled correctly. This code handles invalid input by catching a value error when a negative width is rejected. Instead of crashing, it reports that the input was correctly refused and includes the error message for context. This makes the program respond to bad input in a clear and controlled way. The code reports how many valid test cases passed out of the total tested. This gives a quick check of the test suite's success and helps confirm that the concrete volume calculations are reliable. This script calculates concrete volume by multiplying length, width, and thickness, while rejecting any non-positive dimensions. It checks the calculation against expected results for a slab, a footing, and a thin repair, allowing a tiny margin for rounding error. It also confirms that a negative dimension raises an error, then reports how many tests passed overall. In this lecture, you learn to Define functions that perform specific civil engineering calculations. Use parameters and return values to make calculation functions reusable. And document and test functions with representative engineering inputs. In the next lecture, Lecture B, we will go over text file workflows.
Thank you for your attention. See you all in the next lecture.